Welcome to, I guess, the only ISA Distinguished Lecture for the 2012-2013 academic year. We are very pleased to have with us Daniel Kirschen from the University of Washington in Seattle, Washington, the other Washington, as they used to say, right?
No, you are the other Washington.
And let me very briefly give kind of a summary of his credentials. He's a native of Brussels. He got his undergraduate degree in engineering at the Free University of Brussels. He then moved to University of Wisconsin, where he got a PhD in electrical engineering. Worked in industry for a while, I believe in Siemens and Data Corporation.
Control Data Corporation.
Control Data, and then couldn't resist and went back to Europe, took a position at the University of Manchester in England, where he stayed for 16 years, and 3 years ago he returned to the US as the closed professor of electrical engineering in the Department of Electrical Engineering at the University of Washington, Seattle. His expertise, well, the title gives us some hint. He's interested in all things powers. He has a fairly large research portfolio ranging from renewables, smart grids, security in power systems, and today he will tell us about the flexibility that is required in power systems in order to take advantage or to mitigate the uncertainty in renewable energy sources. Daniel?
Right. Thank you very much, Armin. So it's a great pleasure to be here. I love talking about power systems. And so I'll talk about flexibility in power systems. So first, an outline. You probably all have heard about smart grids. I'll give you a bit of my view on smart grids, what it's all about. Then I'll talk about keeping the power system in balance and the need for flexibility. We then talk about flexibility on the operational timescale. By that I mean flexibility, how do we deploy flexibility with the resources that we have. And then we'll talk a little bit about flexibility in the planning timescale when we have the opportunity to build more resources. So first, if you ask power system operators what their job is about, the first answer you will get is keep the lights on. They want to make sure that the supply is reliable. And let's keep in mind that the power system, it's out there, it's not in a nicely packaged microcircuit, it's not inside a nice box, it's exposed to the elements, the lightnings, the storms, and so on. So keeping reliability is not a trivial problem. But there's another aspect to their job, and that has to do with money. We all pay our electricity bills every month, so you multiply what you pay every month by the number of people living in this country, you get a really big number. So we're talking about enormous amounts of money, so any small improvement we can make in the efficiency with which we deal with the power system has, turns out to a large number. So for many years, that's what power system operation was about, and I like to call it balancing the greed and the fear. Running at lowest cost while keeping the lights on, or not putting little old ladies in the dark. And all of this used to be done by monopoly vertically integrated utility. Then you had to keep the reliability. They could do it as a reasonably low cost. Power technologies were pretty mature, so no real need for innovation. So we got in a situation for quite a number of years, not really much was happening in this field. And then something happened. We decided we need to go green. We need to reduce CO2 emissions. We need to integrate renewable energy sources, mostly wind and solar. So we went from having to balance just the greed and the fear to a three-way competition between cost, reliability, and being environmentally friendly. And we know how to keep the system reliable, balancing the reliability and the cost. But doing all three is much more complicated. We can be green and cheap, but we won't be reliable, or we can be green and reliable, but it's not going to be cheap. So this whole business of smart grid, in my view, is really an attempt to do better in all three directions at the same time, essentially trying to improve the integration between those three competing objectives. Now, smart grids, lots of different definitions. We were talking about that this morning, and on my more cynical days I will say that people will define the smart grid as what they are trying to sell you. But I'll take a fairly general definition to say trying to use communication, control, and computing technologies to enhance the operation of the grid. And the idea is that these technologies are a lot cheaper than copper, concrete, and steel that are the essence of the traditional power technologies. We can do things a lot more cheaply with smarts, communication, control, and computing than we can with building more transmission lines, building more power plants. So that's the whole idea, I think, of smart grids, but different people will define it in different ways. So let's move on to flexibility. One thing that you have to do, another balance you have to have in the power system, which is now a physical balance, you have to have this physical balance between the power that is being produced and the power that is being consumed. And these two must be kept equal, essentially on a second-by-second basis. Now, in the old days, what you had to keep this balance in the face of fluctuations in the load. So over the course of the day, as you see in the diagram there, the load would be minimum around 4 in the morning, and then would start climbing, reach a peak around noon, decline a little bit, and then again a peak later at night when people are watching television. And I think this is a British slide, so it's when they have a cup of tea around 9 o'clock in the evening. You have a question?
So why it has to be exactly equal? Is it because of storage?
It's because we can't store, essentially the answer. It's the ultimate in just-in-time manufacturing. You know, the power that we are consuming now with this computer, these lights, is being produced almost essentially at this time. And if you have this imbalance, well, the frequency is going to drop and the system is going to collapse. So we don't want that to happen. So in the old days, these were the fluctuations we had to deal with. They were, you know, human beings, if you aggregate them enough, are fairly predictable. So you could predict the peak demand for tomorrow with about a 2% error, even including errors in the weather forecast. And the ramps would not be too bad. So relatively slow changes, predictable with good accuracy. So we could schedule conventional generating plants, coal-fired, gas-fired, to balance this load. So no big problem here. But then we introduce renewable energy sources. And here I picked up a couple of graphs showing the output of a particular photovoltaic system on different days. And you can see that you get, well, different days are in different colors. And you can see that different days are different, and even within a day it goes up and down depending on whether you have a cloud or you don't have a cloud. So you have very rapid and hard to predict fluctuations. Here's another example. Things look pretty nice. Sun rises, the output of the PV plant goes up, and then suddenly in the middle of the afternoon you have a band of clouds. It drops pretty dramatically and then restores. It goes back up and back down in the evening. How about wind? Well, in wind it may not be quite as dramatic. Wind fluctuations are a bit more slower, but you still have significant changes. Here you have the wind power of a particular plant or farm in blue. It's going up and down, but this is done with a 15-minute resolution. Now, another thing that you notice is that the green curve here is the demand for this region, and you can observe that it's anti-phase with the wind generation. There are parts of the world where the wind blows at night when we don't use a whole lot of energy, while the consumption is peak during the day. Part of the world where I live in these days has that problem. We get nice wind around 3 in the morning along the Columbia Gorge, where most of the wind plants are located. And you also have problems with forecasting the wind. It's quite easy to forecast what the wind is going to be 15 minutes from now. Your best guess is exactly what it's doing now. But if you try to forecast 24 hours, it's going to be pretty much all over the place. So not easy. So really, if we have a power system with more than a few, cute wind farms or a few experimental PV panels, we may start having some interesting problems. So instead of just looking at the load, now we should be looking at the net load, which is the difference between the load and what is produced by this renewable generation, which is essentially not controllable, which we let produce exactly what it wants to produce. And that net load must be balanced by the rest of the system. So your conventional generators are going to have to respond to those rapid fluctuations, and the amplitude of these fluctuations is going to increase with the amount of renewables that we install in the system. So over the future, we are going to have more problems. And again, we are pretty good at forecasting what the load does. Forecasting what the wind generation, what the sun is going to do, is a much more difficult problem. So, how do we keep things in balance? Well, the standard answer is to say, well, the rest of the system is going to have to be more flexible. But providing flexibility costs money. That's something very important to keep in mind, because this flexibility is going to have to come from conventional power plants. These conventional power plants, to keep them going, to get them going, you have to burn coal, you have to burn gas. If you have to bring online more of these conventional generating plants, it's going to be less efficient. You are going to be able to do a less efficient economic dispatch than you would be able to do if you could just predict what's going to happen and then have to have this reserve to go up and down as the wind or the sun changes. So the first question we want to ask is, well, how much flexibility do we really need? We could just say, I want a lot, because if I have a lot, I'll be on the safe side. And frankly, if you ask a power system operator, that probably would be their response, because they want to play it safe. Remember, reliability comes before cost from their perspective. They don't want to be blamed for an outage, so they want to have at their disposal as many resources as possible. But on the other hand, we are paying the bill, so we don't like blackouts either, but there's a cost to everything. The next question is, okay, let's suppose we know how much flexibility we want. Where should this flexibility come from? Well, typically it would be from these conventional generators, coal-fired, gas-fired. We can ram them up and down. We might also try to get the demand, the consumers, to adjust their consumption in response to the needs. So if the wind is blowing hard, maybe we can anticipate and do the dishes now. If the wind is not blowing, maybe we can do the laundry later. A lot of interest these days is going to storage, developing new battery technologies. That would be extremely good form of storage if it were cheap enough. So chemical engineering, material science people have plenty of work to be done there to make that practical.
Yes. Storage, something they used to do in Belgium, in coal, two lakes, you pump it up in the night and
yeah.
go back down in the day.
Pump hydro is still the more common economical way of doing energy storage, so it can be done. The problem with pumped storage is that the investments required are huge. The environmental impact is significant. There are not many places where you naturally have two lakes and a place where you can put the pumps and the pipes. So it's hard to justify. So it only has to, no, the technology exists, but it's a question of a technology at a reasonable cost.
Is this a one-cost investment, or is it an investment that has to take place over a long period of time?
It's, well, you have a huge, one-time cost of building. For example, one of the biggest in the world is in North Wales, close to where I used to be in Manchester. You essentially excavated a mountain to build that. Okay, that doesn't come cheap. And also, I think that one had an efficiency about 77, 78%. So you have a cost. Every time you pump it up, it's costing you a lot of money. So hopefully with batteries, we'll be able to do better. And then the last type of flexibility is what I like to call virtual flexibility. Power system operator has some operating rules, and these days they operate within the context of an electricity market. Well, those rules and these markets constrain what they can do. And sometimes if we change the rules of the market or the operational rules, we may reduce the amount of flexibility that we have to provide, just by, again, being smart and looking at the impact that these rules have on the need for flexibility. And that obviously would be the cheapest way of providing flexibility. But it needs to be carefully thought through to make sure we don't affect the reliability of the operation. And finally, leads me to the 2 points I want to cover next. There is going to be an operation issue. How do we provide flexibility with the resource that we have? And then looking into the future, how do we decide how much flexibility we need to invest in? Because sometimes, particularly if you're in an electricity market that just pays people for producing energy, they will want to build power plants that just produce all the time and don't provide flexibility. That may not be what the system needs if we have a lot of renewables to deal with at the same time. So let's first talk about flexibility at the operational stage. And running a power system involves a lot of thinking ahead of time. You don't improvise. And there's therefore a lot of scheduling that takes place. They think a lot today about what they're going to do tomorrow, because a lot of the power plants that they use are large coal plants that don't start fast. And to start them, you have to invest a lot of money in getting them going. So there's a lot of, in essence, an investment cost of getting that plant going tomorrow. So the question then you have to decide is, which plant mix do I want tomorrow? I would want, on one hand, I would want to run my most efficient plants, but on the other hand, I also want to have available the plants that I will need to go up and down as I face some uncertainty. So I need to figure out how much uncertainty I will face tomorrow, and then once I have an idea of that, trying to optimize that, to do some kind of optimal scheduling calculation to decide which generating units I should start at what time.
Was the location of the plant matters too?
Yes, because there's a network. But at this point, I'm going to ignore the network. I assume that I have a copper plate, that the electrons can go from any plant to any load for free, yes. The real life is more complex than that, I grant you that. But for looking at flexibility, we'll ignore the problems that the network add. So what data do I have to make those decisions? Well, okay, when I'm today looking at tomorrow, one thing I'm going to look at is what kind of forecast I have. I'm going to have a forecast of the load. I'm going to have some kind of forecast about the weather. But the resolution of these forecasts tends to be, 30 minutes at best, typically more likely to have 1 hour. And so that's going to be useful to schedule the slower flexibility. What unit do I need on at what time? When do I need to turn them on? If I want to deal with phenomena that happen faster, for example, you saw the rapid changes in wind or in solar generation, well, I would need to have higher resolution data. But there I can't use forecast. Nobody is going to tell you, at 8:13 the wind is going to pick up. That would be complete guessing. So we have to use some kind of historical data to tell us, okay, this is the type of fluctuation that we usually see at this time of the year, at that time of the day, so we need to be ready on a statistical basis to deal with this type of events. So this is what we have been doing recently. My student and I got some data from Texas, where we got, I think, several years worth of 1 minute resolution net load data from the ERCOT interconnection in Texas. Essentially, we know what wind generation there was and what load there was, and we therefore can calculate the net load with 1 minute resolution. And that's the blue curve. But then you have where the schedule for the market was saying would be happening at each hour. And the difference between the red and the blue is the flexibility, the short term, the intra-hour flexibility that we need to deal with. We assume that the market will take care of what happens every hour, but the system operator has to keep the system in balance in between those hours. And so that's, if you do the difference between the blue and the red, you get a little diagram up here that shows the minute by minute over every hour. And we assume that at each hour we are back in balance. And again, we look at the flexibility needed for the next hour. So we take this whole several years worth at 1 minute data, and we analyze this data. And we look at these variations. And really we look at three things. We look at, sometimes we need an increase or a decrease. So there's a question of capacity, megawatts. We have the rate of change, or the ramp rate. So that will be megawatts per minute. And whenever we have one of those ramps, we also want to know for how long it lasts. So we analyze this data to look at events, and we represent these events by triads involving capacity, ramp rate, and duration. And then if we can plot that in a three-dimensional space, and we get a cloud of points like here, representing the type of variability event or flexibility event or lack of flexibility event that we had over this whole period. And if we have enough data, we get a probabilistic representation of what we should be able to deal with. So what we want to do is optimize the flexibility that we want to provide. So we look at each of these data points and we try to figure out, okay, should we include the ability to deal with this data point in our schedule for tomorrow? Or is this so rare that we decide it's not worth dealing with? So really we are looking at doing a trade-off between the cost of providing this flexibility and the cost of not providing this flexibility. Now, the cost of providing the flexibility, well, there are really three parts here. We have, the cost of producing the energy, the cost of the upward flexibility when we have an upward change in net load, cost of going down. Then we have these two other terms. ENS is the expected energy not served. So that's a probabilistic measure of how many customers we will put in the dark for how long, because we don't have the resources needed to satisfy these customers. And we multiply that by a factor called the value of lost load, which is essentially a dollar value we assign to putting people in the dark for so long. And then another thing that can happen is that we may have to spill some wind. But because these days the assumption is that we will not spill wind, if you do spill wind, you have to pay the wind generators for not producing. So there's another term there that's kind of a compensation for these wind generators when you tell them, sorry, you really have to cut back on your production. Economists don't really like this, but that's kind of a policy decision that has been taken in many parts of the world that we are going to use all the wind that is being produced.
So this is part of the contract between the wind generator and?
It's part of the law, essentially. When different states have come up with these renewable energy mandates, they essentially say the wind has a right to produce, has a right to inject in the grid everything that they are producing. And because those wind producers have invested so much in building those facilities, and because the wind is free for them, if they can produce, they want to produce. And if you tell them no, they are not happy.
Why isn't it not the same argument with other producers?
Politics? it's yes?
How involved the cost of the flexibility? It's just use the optimum cost of the requirement of the flexibility to get the cost.
What we do is essentially we run some what we call a unit commitment calculation, and providing this up flexibility is going to require us to run more generating units. So that's going to add some cost to.
You mean you write the unit commitment with the flexibility and without the flexibility?
Yes.
And you just
That would be essentially the way to define it.
okay.
Yes. So we essentially, for each data point, we decide where do we want to do this, and the last data point we decide is worth including sets or flexibility requirements for intra-hour flexibility. And if we do this for the data, this is some types of results that we have obtained. Flexibility, I haven't really talked about this, but can be secondary or tertiary flexibility. Tertiary is a bit slower than secondary, but let's just look at secondary. The green is the up flexibility, the red is the down flexibility. The upper graph there is the capacity, the middle graph is the ramp rates, and the lower graph is the duration of the events. And along the horizontal axis we have the 24 hours of the day. So you can see that in the morning we need a lot more up flexibility than downward flexibility, because typically the load is going up at that time of day, so it's unlikely that we'll need to back down the generators because the load is taking care of that. And then we have bigger ramp rates at this time of the day than later. And the duration tends to be about constant. Now this doesn't show something. We also looked at the seasonal effects. There are times of the year when your wind tends to be, not just blow more, but also changes more rapidly. And being able to adjust those requirements depending on the time of the day and the season of the year could represent quite a substantial saving. Because if you put the same blanket requirement across the year, sometimes you will have too much, sometimes you may not have quite enough. So this is the kind of work we do in terms of flexibility at the operational stage, dealing with the resources that we have. With some students at the University of Manchester, we also looked at flexibility at the planning stage. And then the question is, how much flexibility do I need to build to accommodate the renewables generation that I expect in a certain number of years? if the renewables, amount of renewables keeps increasing, I will probably need to have more flexibility. I want to make sure that that flexibility is available when I need it. And now we are not looking just at minimizing the operating cost, but we're also looking at minimizing the investment cost. So essentially we're looking at minimizing the total cost, balancing operational cost with investment cost. We might be able to accommodate with less flexibility, but that might really raise our operational cost. And we could build too much investment, to build too many facilities, so spend too much on investment, but then we have very low operating costs. So we have to balance the two. So for this analysis, we made some assumption. We assumed that we are still dealing in a centrally planned system, so that we don't have to deal with the complexity introduced by an electricity market. We're just looking at, assuming that somebody is looking at the whole picture and can decide how much flexibility needs to be built. We're only looking at flexibility provided by the generation. We can extend that work. We've done some of that since to introduce also flexibility from the demand side. So we're really looking at how do we compare different types of generating units in terms of the ability to provide flexibility. And the basic tool that we started from is the unit commitment. Now, the traditional unit commitment problem has to deal with scheduling generating units to minimize the operating cost. So essentially, you assume that you have a fixed set of generating units, and you can pick which one you are going to start at what time to meet the load profile like I showed you earlier. And that's done with a certain number of constraints, certain number of dynamic constraints, for example, up and down ramp rates, and minimum up and down time, which is essentially the number of hours the unit has to stay on when you turn it on, and the number of hours it has to stay off when you turn it off to avoid damaging the plant. So we have some of those dynamic constraints. So we're really looking here at intra-hour flexibility, deciding how much flexibility we need at each hour. Now, as in any optimization problem, if you give yourself more resources, you're going to reduce your objective function. You'll be able to do a better job at meeting the constraint at a lower cost. But this traditional unit commitment ignores the investment cost. So, and it typically only looks at 1 day to possibly 1 week. So it's a starting point, but really what we want to do is to enhance this unit commitment to consider both the operating cost and the investment cost. And the idea is that we are no longer going to consider just a fixed set of generating units that are built, that are available. We're going to consider a variable set of generating units. And so our decision variables are going to be not just is this unit generating at this particular hour, but also does this unit exist? Have I taken the decision to invest in this generating unit? And backing up one of my bullet points there, because I am looking at investment decisions and I'm not going to build a power plant just to run for a day or a week, I need to run this over a much longer period of time to see whether building that power plant is justified under a variety of conditions. Because there might be seasons where it's worth having, might be seasons where it's not a good deal. So all of that needs to be taken into account. And typically unit commitment is these days is solved using mixed integer linear programming problem. It's already a challenging optimization problem when it's run normally on a large system. But now I have added these extra decision variables of whether a unit exists which was not in my original traditional unit commitment. So I have really expanded considerably the size of the problem. And if you have done mixed integer linear programming, you can think that I'm heading for trouble here. Okay, first thing we had to admit is that we were not going to be able to run this enhanced unit commitment for an entire year, considering the 8,760 hours that you have in a year. We decided, okay, what we need to do is to use representative weeks of what happens in winter, what happens in spring, what happens in summer, and again in the autumn. And the colleagues at EDF, Electricité de France, with whom we worked, also said, well, we also want you to consider an extreme week. A week that happens once every 4 or 5 years, where we have a very high demand or very large fluctuations. And we stuck that extreme week between winter and spring, right there. So essentially we are considering 5 weeks. We don't give them all the same weight. We have more summer weeks than winter weeks, and we have very few extreme weeks to keep things balanced. And then we used some clustering techniques, looking at the net load data to identify the most representative weeks that we needed to consider in this optimization. Now, as I said, mixed integer linear programming is wonderful, but if you're not careful, it's going to blow up in your face. So we had to do a bunch of things to keep the lid on the CPU time. The first thing is reduce the number of decision variables. Well, essentially we said, let's assume that some of the generating units, we know they are there, they're already built. We don't need to consider those, because that would just make life more complicated than it needs to be. We could also start from a reasonably adapted system. If we know what the peak load is going to be, we don't want to have 3 times as many candidates unit as this peak load, because that gives too much flexibility. So we should start, have a rough idea of how much capacity we should be considering before we start the optimization. And then another thing that happens in power systems is there are lots of units that have essentially the same characteristics. Well, if you treat them all as independent units, it's essentially going to churn to lots of combinations that are essentially the same. So we developed this priority ordering constraint that said, if you have units that are essentially the same, always use them in this order. 1, 2, 3, 4, 5, instead of trying all the possible combinations. That also cuts dramatically the number of combinations that we have to consider. So this is some test results we got with this analysis. We had a 26 unit system. Some of these units are what we call peaking units, which tend to be the very flexible but rather inefficient ones. The black units are the big nuclear units, so they are very efficient but very inflexible. And then we have some blue units, which are somewhere in between the two. And the question is, okay, which of these units should we rebuild? Well, we first started with some different load profiles, kind of checked that our optimization gave results that made some sense. So we have an original load profile, a load profile we made a bit smoother, and a load profile that we made a bit sharper, with the idea that the sharper load profile would require more flexibility than the smoother one. And we checked that if with the original load profile, the first row in this table, we should use those 26 units we had, we should probably do without unit 1 if we had a choice. With the smoother load profile, which also has a more energy demand, we should have all the units. And a sharper one, we should keep unit 9, but take units 2 and 5 out. So that was just the point of checking that things were kind of working naturally.
So how do you know that this makes sense?
Intuitively, it does make sense, because Unit 9 is one of those very flexible units, so it's going to be quite useful when we have those sharp transitions. Unit 2 and 5 are more intermediate units, so less useful in this case.
Is the conclusion then that it's quite sensitive to the profile? Because I mean, if I look at the picture that you had in the previous slide, right?
Mm-hmm.
It looks to me that, sure, there are variations, but they don't seem to be that large.
Right, okay, here we are, the first part I was talking about, intra-hour, very short flexibility. Here I was looking here at some inter-hour flexibility, which is a bit slower type of flexibility.
So that is the reason why you see this difference?
Yeah. So the next thing we try to do with this is, okay, what's the impact of wind generation on the flexibility requirements? And there we need to look, there are different things that happen at the same time. So we have to try to separate them. So first, if you have more wind generation, well, it's going to displace your conventional generation. So the energy requirement is going to go down. The next effect is that because wind is harder to predict, we are going to have to provide more reserve, more essentially units that can ramp up and down. And so the traditional criterion for reserve would be that you would provide as reserve the capacity of the largest unit that is currently connected to the system. But when you have uncertainty due to the wind, people have suggested that you should add 3.5 times the standard deviation of your forecasting error. Just as a rule of thumb, we are trying to refine this through our work in the intra-hour flexibility, but we hadn't done that yet when we did this work. And the third phenomenon we have to consider is because we have those fluctuations in wind, that in itself will increase the need for flexibility. So we came up with 4 test cases to look at these effects. So the case 1 is our base case, where we have no wind and no forecasting error. Case 2 is essentially adding the wind, but assuming the wind is nice and constant, which is totally unrealistic, but it's a way of separating the cases. And also assuming we have a pretty good idea of what the forecasting error is going to be, so a sigma of 0.1. Third case, we have 10% wind, but then we consider this wind is going up and down, but still good forecast. And the fourth case, we assume 10% wind, but no fluctuation, but then we have more error in the forecast. And we were pleased to see that for these different cases, we came to different, optimal portfolio of generating units. So you can see that some units are definitely not needed. For example, unit 13 tends to be out most of the time, but depending on the other cases, different sets of units are what is required. Now the case number 2 is, as I said, it's just a wind where you just essentially are cutting 10% off of your needs for generation. Well, obviously that's the one where you would need the smallest number of generating units, so you could remove these from your set of available generating units. So, time for some conclusions. I think I've argued that it's important to quantify how much flexibility the power system needs, because as I said, providing this flexibility costs substantial amounts of money. And these flexibility requirements are going to depend on the amount and type of renewable generation. I've kind of mentioned both solar and wind. They don't have the same stochastic characteristics. So depending on whether you have a lot of wind or a lot of solar, the flexibility requirement will be quite different. It also depends on your system, the rest of the system that you have, the load profile that you have, I mentioned in the Pacific Northwest, the wind blows at night. In other parts of the world, it blows at different times of the day. That depends on your geography. And also, these flexibility requirements are going to depend on the season, the day of the week. You don't need the same flexibility on a Sunday as you do on a Monday, and the time of the day. That's also quite important. And I also argue that optimizing the flexibility requirements could save a lot of money in operational cost and in investment cost, while hopefully keeping the reliability of the system high. So in terms of looking forward, where are we going? Well, currently the industry is quite a conservative one. They like to do things the way they have always done. They tend to have fixed flexibility requirements. Well, if we could adjust these flexibility requirements depending on the time of the day and day of the week and season of the year, that could already be quite interesting. We need to look in more details at how the flexibility requirements are going to change as a proportion of renewables increases. And that's not an easy thing to do, because it's going to depend on where we build them and how much correlation there is between the different wind farms. One thing to keep in mind is, the big cost in a wind farm is the cost of building it. Once you have built it, you want it to run as much as possible, so you want to put it in the place with the most wind. And that's the reason why the wind farms tend to congregate all in one place. And then you get a lot of correlation between the wind in that region. If we can have a place where they are in different locations or connected by transmission, you can aggregate over a more diverse pool and therefore reduce the problem associated with the need for flexibility. But that's hard to predict as we go forward. So I talked about flexibility in the operational timescale and the planning timescale. Well, so far they have been treated slightly differently. What we need to do is try to bring the two together based on the work that we do on operational time frame, introduce that into the planning time frame. And also we need to look at not just flexibility from generating unit, but also what we can do with the demand side, with storage, and then with market rules, and how these market rules affect the need for flexibility. So I want to acknowledge the people I have worked with on this, both at the University of Manchester, Juan Ma, who was one of my PhD students, Nando Ochoa, and Angel Rosso, who did a master's degree with me there. And at the University of Washington, my current PhD student, Yuri Dvorkin, and my colleague, Miguel Ortega Vasquez. Thank you very much.
Let's open the floor for questions.
Yeah, I was just wondering how realistic in the future would it be to borrow wind energy from other locations. They're abundant in wind.
There's already an awful lot of that going on. For example, the state of California has been quite aggressive into setting renewable targets. Okay, they have a fair amount of wind in California, but sometimes there are better wind resources somewhere else. So they can they're hoping to import that into California. But then you get into the question, okay, that means there is enough electricity transmission capacity to do that. Do we want to build transmission to bring renewable resources in different parts of the world, the country? I have to start saying transmission lines are ugly. I think we all agree on that, but they are extremely useful because they allow you to do this aggregation over a much bigger region and this economic optimization over a much bigger region. So that has a lot of value. So we get into this interesting conflict between, economics and reliability on one side and, the environmental impact of having a transmission line, or balancing the fact that you can use more renewable resources if you have this transmission with the fact that transmission line is ugly. It's not an easy one. That's a really political decision. Yes?
Like you mentioned, as we get closer to our goals of having a higher percentage of renewable energy resources. For instance, California, I think, wants to have 30% renewable energy by 2020. So to guarantee the kind of flexibility you talked about, you need fossil fuel plants.
Right.
And so that goes against the goal that we have.
That's right.
So it's not a scalable thing. And therefore, it seems like you need flexibility at the consumer end at some point, right?
That's right.
You need flexible load. So if you could sell electricity that isn't guaranteed to be coming all the time, then the consumer would pay less. And if you can get enough consumers to go along with that, that balances the uncertainty in the generation.
That's right. So that's also a very active topic of research. What can we get from the demand side?
Right.
And
do you think that that's necessary down the road?
I think so, but I'm not sure yet about how much potential there really is, or how much are we willing to sacrifice comfort to make our load flexible. And there are things that are just not flexible. The lights here, your television during the Super Bowl. It's not an easy one. It's the kind of thing where you might need a big shock to realize, yes, we need to do something about this. But it's not easy. So that's why people hopefully look at storage and hope for technology development in storage, because that could make a real difference.
Yes.
Yes.
You mentioned 3 factors at the beginning, and green was at the top. But the talk somehow assumed that more renewable is better, is basically adding to green, right? Implicitly.
Implicitly, yes.
But is that really a good assumption? And one. And two, isn't there a quantization effect, which means that it's not necessarily the case that although the relationship is monotonic, that it's strictly monotonic?
You're perfectly right. It's in essence, I say we do a lot of optimization, but in this optimization, essentially the amount of renewables is not one of the decision variables. We kind of take in as given that they will happen. It's not optimized. That's kind of one of our premise. Political decision, it happens. We have to deal with it. Whether that is the right thing or the wrong thing, we haven't really looked at that. But you're entirely right. More renewables may not always be the right thing. As you said, sometimes a lot of renewables, you may end up burning a lot of coal, which is not good. I'm afraid that I'm just looking at my view of the problem, which is limited in its scope.
And one technical question: you had sigma was 0, then 0.1, 0.3.
Yes.
0.1 was small, 0.3 was, I guess, large.
Large, yes.
But why? In relation to what?
It was just,
In relation to the mean, or?
It was a measure of the uncertainty on the forecast for wind.
But was that absolute or relative?
Relative.
Relative to
Yeah,
the mean.
to the mean, yes.
Any other questions?
Aren't microgrids supposed to mitigate this problem to an extent? So if so, has there been any study on how it gets done with those?
Okay, let me bounce one question back at you. What do you call a microgrid?
I mean, a group of loads and renewables hooked up together to serve each other.
Right, okay. So if you define a microgrid essentially as a group of people or organization that realize they have a mutual interest in optimizing as a group, I think there's potential there in the sense that it makes them more aware of what needs to be done and what can be done. Okay, they realize that they can balance this against that, and overall they have a better, let's call it a better energy profile. That's good when people start being aware of that. But in a way, what we need to do is that aggregating over a large number of people. You know, if the microgrid is kind of inward looking, just looking at it for us, I don't think that's very good. I think we have to look at, you know, everybody doing a piece, and that's when I talk about demand response. Essentially, I'm looking at doing that on a much bigger scale, where everybody gets to participate or has to participate.
One quick question: do these exist, microgrids?
You have, in special circumstances, they exist. You could say that, you know, a small village in Alaska is a microgrid, right? Because they have their own little town generator and they have the local loads, and they know that they can't all turn on all their loads at the same time. So that's microgrids. At the other end of the technological scale, you will have, you know, the US Army has realized that maybe they want their army bases to be, you know, self-sufficient or have the ability to be self-sufficient and operate as a microgrid. Occasionally you have, particularly in places like Denmark, they have thought about, you know, there's a municipal swimming pool, then you have a co-generator. It's small enough that somebody can say, yeah, let's do a little bit of local optimization. But I think macrogrid's a bit of a fad, except for special circumstances. I don't think they are the answer to the problem. Yes.
I'm wondering in your presentation now about there are 4 cases about when how forecast error. There will be non-fluctuating and with fluctuating and also with forecast error. I'm just wondering if there's no fluctuating, where's the forecast error come from?
Right, it was coming from the fact that we were simply adding a certain amount of reserve to deal with the uncertainty. Okay, so you have the here you have, you know, the need for reserve comes from dealing with the forecast errors. That's just giving yourself some flexibility to the fact there's unknown there. And then there's flexibility for just going up and down in a way you expect. It's, you know, dealing with variations you expect and dealing with variations that you don't expect, but you know might happen. Okay.
More questions? Before we close, I want to thank you for a very interesting talk. Tomorrow, 9:30, we will have the roundtable in the ISAR conference room on the first floor. That's I believe room 1104. If you need rooms, you're more than welcome to join us. And it'll run till approximately 11 o'clock. Any good words? Let's thank the speaker again.